Uh, uh, Hello, everyone. It's a great pleasure to be here. And my name is Rui Zhang. I'm from National University of Singapore. So this is the paper I'm going to present today on behalf of all the co-authors listed here. Its title is Intelligent Surfaces Empowered Wireless Network, Recent Advances and the Road to 6G. So in this tutorial paper, we first give a discussion about the historical development of intelligent surfaces. As you can see, right, it's dated early 2000, starting from some metal materials like such as metal films. But as you can see, early studies on intelligent surfaces mainly focus on the hardware aspects, right? For example, the digitally controlled metal surfaces. And only in recent years, right, starting 2020, and the wireless communication researchers have started to realize is a potential in reconfiguring wireless channels. And with this new application, becomes quickly very popularized in the wireless communication community. So what is intelligent surfaces, or some people call it intelligent reflecting surfaces or reconfigure intelligent surfaces? So basically, you can think about is a better surface, and it has many tiny reflecting elements, typically at the wavelength size. And we have a smart controller, and the controller is able to control each of the individual the reflecting elements, the amplitude and the phase. So collectively, it can form, a different reflection beam patterns, and by this way, you can reconfigure the wireless channels as you wish. So ICE has already found many important applications in wireless communication. For example, you can deploy the surface in the environment to bypass the obstacles to create the virtual line of sight channels. You can also deploy the environment to introduce additional multipass and to enhance the MIMO channel rank and also the distribution to improve the spatial multiplexing performance. You can also use the IS as a passive repeater or relay in the hotspot area to cover the indoor users. Or you can also use the surface to cancel the undesired interference from adjacent cells. So here I want to compare the RS with the current technology, Massive MIMO, which has been primarily used in 5G. So Massive MIMO, the main benefit come from the use of a massive number of antennas at the base station, such as can form very narrow beam to pointing the users, such as you can achieve very high beam forming and spatial multiplexing gains. However, there's an issue with this technology that says if we scale the number of antennas at the base stations, that also comes with increasing the energy consumption and hardware costs, as well as the processing complexity, especially when we evolve into the higher frequency bands as millimeter wave or terahertz. On the other hand, intelligent reflecting service can help us to achieve a small, even a medium MIMO. The reason is because by deploying the eyes in the environment with a very large aperture, and the base station does not need to form very narrow beam. Actually, it can form even broad beam towards these intelligent surfaces. And by using the reflected beam forming, and they can form narrow beam to point users. So by this way, eyes can help substantially reduce the number of antennas and also the implementation complexity and cost in the future base stations in 6G. However, this gain of eyes does not come for free. It also introduces new design challenges. For example, how to design the reflection coefficients, right, of the large number of reflecting elements, right? Because in the practical network deployment, we not only have a single eyes reflection, we may have multiple eyes reflections. And the eyes reflection also need to be jointly designed with the base station beam forming. So this is a very gigantic and hard, optimization problem. And also for eyes to achieve its best performance, it also needs to be a wide channel with the base station and also with its covered users, right? So this requires a new channel acquisition, either in the form of instantaneous channel or statistical channel, but this all comes with additional cost. And thirdly, right, how to deploy the IS in the environment, right? Whether we should deploy the base station side or is that the user side, and whether we deploy the IS in the centralized with a large surface or with a distributed manner with many small surfaces. And all of these questions need to be addressed. So in this tutorial paper, actually, we report the state-of-art solutions to tackle all of these problems. So if you're interested, please take a look of the paper. And this tutorial paper will also introduce some new and emerging, I think, quite interesting applications of RS. For example, we can deploy the RS on the target. For example, here you can see the UAVs, right? So help the UAV to achieve more efficient sensing, all right, and localization. And we can also deploy the eyes and some high mobility vehicles, for example, the cars here, and such as to form a strong virtual alliance sign link, and such as to reduce the multipass feeding effect in such high mobility communication scenario. We can also use eyes in non-terrestrial networks, for example, at the satellite, use it as an antenna array, passive array, or at the ground terminals, to improve the link budget for the satellite communication. We can also deploy the RS, inside the base station, right? Either at the side or in the front, with multiple layers, for example, the stack intelligent matter surfaces, and such as you can think we can form this passive virtual arrays, to assist the active antenna at the base station to improve the beamforming performance. And in this tutorial paper, we also discussed the recent 60 standardization activities for intelligent surfaces, and also the practical deployment approaches. So actually, there are two main approaches, as you can see here. The first is the so-called base station controlled RS or RIS. And the idea is that the base station will, through a separate link, to directly control the operation of the RS. And this can be easily implemented, right, by using the existing standards, for example, the NR smart repeaters or network controlled repeaters, NCRs in the 3GPP. And but the drawback of this is that you have to spend additional network resources for the base station to control the IS, right? So this increase the network control overhead. Well, the other approach is easier to implement, is called self-controlled RS. So in this scenario, the operators, right, and also the users can deploy the IS as they wish, and then they implement their own controller, right? So the IS can operate without any interaction with the base station. So you can think of, in this case, the IS is just some environment, auxiliary devices deploy the environment to improve the user's performance. And the good thing is here is that you do not need the dedicated control signaling from the base station, and simplify the realization. And at the end, this tutorial paper also introduced, other recent development for advanced MIMO. For example, for RS, not only we have reflecting mode, we also have refracting mode. We have, instead of a passive IS, we may have an active IS. Also, like about advanced architecture, like beyond diagonal IS and so on and so forth. We also introduce as other relevant technologies, for example, holographic MIMOs, dynamic matter surface antennas, and more recently the 60 movable antennas, where the base station antenna arrays, you can flexibly rotate and reposition them to match the 3D user traffic, and such as you can improve the network performance. Okay, so with that, I think I should stop here and leave more time for the Q&A. Thank you.